Thank you for coming. I'd like to introduce Martin Odersky from EPFL. Martin was one of the people responsible for the addition of generics to Java, and he's been doing a lot of interesting work with programming languages, and he's going to tell us about his work with Scala.
Thank you. Okay. Can you hear me like this? Barely. Barely? Okay. Okay, I put it a bit up. Better? Yes. Okay, thank you. Okay, so thanks for the nice introduction and the invitation to give a talk here. I'm going to talk about what we worked on over the last, 5 years and what we have released over the last 2.5 years, which is a very big experiment in language design and also in language adoption. The language is called Scala, or Scala in the American pronunciation. And so the original question was, can we design better languages for component systems? I'm going to start my talk that way, but really Scala now is probably more than that. I believe it's a language which is really very nice to use in a lot of contexts, component systems and other systems as well. But for component systems, that's what we try to do first, and so we're going to talk about that. So if you look at the state of the art in component systems, then it's actually pretty miserable. So in principle, our principles are clear. Software should be constructed from reusable parts. Markets for component systems have been postulated 10 years now that you would have a market like for hardware parts where we have suppliers of components and customers of components and all that. In practice, very little of that has come true. So most software is still written from scratch, more really like a craft than an industry. And because I'm a programming language person, so I have to look at programming languages, and I have to see that programming languages, oops, shouldn't talk to. No, it's not my fault, right. So programming languages share at least part of the blame, I believe, because most existing languages offer only very limited support of components. And ironically, this holds in particular for the languages that have been pushed hardest as component languages, namely statically typed languages such as Java or C#. Things tend to be a bit better in dynamically typed languages such as Smalltalk, Python, or Ruby. They actually have more flexibility to do components than in static languages. So we'll see why that is in a minute. Oops. So the question is how to do better, how to improve on the state of the art. And we started our work on 2 hypotheses. The first one is that languages used for components obviously need to be scalable. That means you should have a common set of concepts in which you can describe small parts as well as very, very large parts. The question is why do I think that? And I think the answer is simply because the parts vary so much in size. A useful component could be a 10-line object or a 10-line function. It can also be a 100,000 or a million-line thing. So once you start saying, well, we have a language for small things and a language for large things, where maybe small things are up to 10 lines, large things are up to 1,000 lines, then you will need to introduce another abstraction for things up to 10,000 lines and another for things up to 100,000 lines. So it's clearly self-defeating. That way you get a lot of different constructs which don't really play well together. So the second question was, how do we achieve the scalability? And there our hypothesis was, let's try to generalize and unify functional and object-oriented programming. And we'll see in the end how it worked out. It's an experiment after all. So, but we must have had some reasons to unify FP and OOP. What were the reasons? Well, I think the 2 areas really have quite complementary strengths for composition. Functional programming, it makes it very easy to build interesting things quickly from simple parts using things like higher-order functions, algebraic types and pattern matching, parametric polymorphism. So you can quickly get something off the ground there. Object-oriented programming, on the other hand, makes it very easy to adapt and extend complex systems using subtyping and inheritance, dynamic configurations, because objects, the basic components, can be rewired as you want at runtime, and also often overlooked in the functional community. Classes are really incredibly useful, this idea of partial abstraction, that you just define something and you implement what you can, and what you can't implement, you just leave abstract and you delegate to subclasses. This is very, very nice, actually. So in summary, functional programming is very nice to get something quickly from simple parts. Object-oriented programming is very good to adapt and extend existing systems. So the question is, if we combine the two, what do we get? Well, that's sort of the theory, but in reality, my reason for wishing to combine functional and object-oriented programming was that I didn't want to sit anymore between two chairs. Because what happened in almost all of my professional career before was that everybody says, no, this guy doesn't belong to us. For the functional programmers, I was this guy doing objects. A bit weird, but yeah, not dangerous. And for the object-oriented guys, I was this functional programmer who said, well, this is this theoretical guy. We can ignore him. It's safe to ignore him. So I was tired of sitting between the chairs, so now I want to show that really object-oriented programming and functional programming, they do indeed go very well together. Maybe so well that at the end you don't even want to distinguish them anymore. You want to talk about. I think the distinction between objects and functions is really by now fairly moot. So to come to Scala, Scala is an object-oriented and functional language, and its other characteristic is that it's completely interoperable with Java. There's also a .NET version, which is currently under reconstruction. That means that it lags behind in the versioning. The latest version currently exists only on the JVM. So what we did is we removed first some of the more arcane constructs of these languages, such as, I believe, static members of classes. That's something pretty arcane. And we added instead, from the object-oriented side, the idea of a uniform object model that's been well proven in a lot of languages, starting with Smalltalk. From the functional side, we added pattern matching and higher order functions. That's sort of your standard constructs that you see there. And what we did not only take things that were known from before, but we also found out in the course of the project's new way to abstract and compose programs. And I'm going to talk more about this. So we have an open source distribution of Scala out since January 2004. Version 2 is out since, I think, January this year. And we currently have about 1,000 downloads per month. So it's reasonably popular. And the community is currently in train of building. So people are starting to do big projects in Scala. There's some big British government websites running with Scala. People are starting to do tools. So for instance, we did an Eclipse plugin, but people at NetBeans are actually doing a plugin from Scala. People at IntelliJ are also doing a plugin. So that shows that actually there is interest in people. The important thing is that people get so far that they're willing to invest some of their time, because otherwise you just push and push and push and push, and people say, no, 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 we want more and more and more, and it's self-defeating. Okay. So in the following, I'll show you three. I can't show you the whole language. That way I probably would need 2 hours, and you would grow tired. So I'll just pick 3 examples where formally separate concepts of functional and object-oriented programming are now identified, and this fusion leads to something new and interesting. So what we are going to look at is how we unify the idea of algebraic data types and pattern matching in functional languages with the class hierarchies of object-oriented languages. We're going to look at functions identified with objects. Functions are objects. That's very close to the proposal on closures that Neil is currently working on. And finally, we're going to look at programming in the large, how modules go with objects. And, well, actually, how modules and objects are just two coins of the same, two sides of the same coin. So first, unification. ADTs, algebraic data types, are class hierarchies. That's actually the most controversial one. So if I talk to object-oriented programmers and I said, well, we add higher-order functions, we add parametric polymorphism, and we add pattern matching, I say higher-order functions, sure, we have them in Smalltalk, well, sort of. And parametric polymorphism is also no problem. We have them. We have that in EPFL. But pattern matching.
Sorry, VC request.
Okay. But pattern matching, go away. That's just not object-oriented. So the common objection are pattern matching are not extensible. Pattern matching are impure because they break the purity of the object-oriented model. And finally, pattern matching breaks encapsulation. Let me go back. So that's the objections. No extensibility, violation of the purity of the OR model, breaking encapsulation. And that's why pattern matching is universally rejected by object-oriented programmers. So I have to show you how we do that in Scala. So here's a very simple example of how we do it. We have here a definition of a binary tree of an arbitrary element type. So, oh, sorry, that was a typo. This should read abstract class tree of T, where T is a type parameter. So we write type parameters in brackets rather than angle brackets as in Java and C#. Then we have two cases. The first is a simple object, empty, which is just a singleton thing, which is an extension of tree. And the other is a class binary of an element and a left tree and the right tree, and that's another extension of tree. And the case modifier, that's special. That actually means that these are classes I want to pattern match on later on. So that's the only thing you need to add to be able to do pattern matching. So here you have a standard function over these things that would be an in-order traversal function. So it takes an arbitrary a tree of arbitrary element type T, and it gives you back a list of T. And then you have a match statement that says that matches the given tree T with a bunch of patterns. Here we have two. The first would say, well, in the case where the tree is the empty tree, return the empty list. And the second says, in the case where the tree is a binary tree with an element E, a left tree L, and a right tree R, so the choice of these variables is, of course, completely arbitrary, respond with in-order traversal of L followed by the E node, seen as a list, and the in-order traversal of R. So these triple colons, they are just list concatenation operations, standard methods in our list class. OK, so far so good. So, yes?
Why T match rather than match with T? Why the postfix?
I think that's mostly historic. Match used to be a method in the object class. And actually, you still can see it like that, sort of, because this infix thing, any infix operator is seen as a method, as a method call of, usually it's left operand. Some infix operators are method calls of their right operands, but they are syntactically different.
I would think that comparing it to a critical switch statement.
Right, yeah, true. So there's a slight syntactic difference. Please, if there are questions, ask while we go. It's probably better that way. OK, otherwise everybody can read that? It's good. So you can argue that this design really keeps the purity because all cases are classes or objects, and that's all we're dealing with here. It keeps extensibility because, well, we've seen two cases here, but you're completely free to define, let's say, a third case called ternary for a ternary node somewhere else in a different compilation unit. Nobody requires you to list all the cases together with the tree, so extensibility is maintained. And also you maintain encapsulation because the pattern matching only reveals the constructor parameter. If any of these classes had fields, they could of course have fields, then these fields would actually not form part of the patterns. So you can still have private fields, and pattern matching does not reveal those fields. All it does, it tells you how this thing was constructed. So pattern matching is just the reverse of object construction. That's all it is. And the other argument would be, well, if you don't want to reveal the constructor parameters, because maybe for safety reasons or because it's too expensive, because, of course, revealing them means we have to keep them around somewhere, then just don't use case in front of a class. Yes?
Some kind of runtime exception if you don't have coverage.
That's right, yeah. So if we had like a ternary tree and we don't have a case in order and we run it on that, then we get an exception called a match error. Yeah. Yes?
One last question. The thing that looks like a non-ASCII character,
Oh, yeah, right. That's equals greater than. Yeah, right. That's my, all these things are, I have this preprocessor which typeset Scala syntax, and it does that automatically. Yeah. You can also use right arrow as a Unicode character. So there's very limited Unicode support in there. But you can use the right arrow Unicode for the same thing. So it's legal to write it that way. Yes?
You match against multiple values at once?
Yes, in a sense, yes. But you have to wrap them up. So there's a class of pair and triple and tuple 4 and tuple 5, which gives you just like a pairs and triples and so. And so if you want to match against two values, you say pair of AB match, and then you say case pair of pattern 1, pattern 2, pair of pattern, all these patterns have to be pairs. Patterns can be nested freely. So here we see only one level of pattern nesting, but you can have patterns inside patterns. Yes?
Is in order a generic method on the type parameter T?
Yes. Yeah. Yeah.
So if you only match on the constructor arguments, it seems it only makes sense with immutable classes.
The constructor arguments are always immutable.
No, I mean, but if you change the object after it's constructed,
Yeah.
then you still match on the original.
That's right. Yeah, that's correct. Yeah. We are actually currently looking at a way to make it even more general, and then you could do things, the things you wanted also, but that's not done yet. Yeah.
Are you mapping on the arguments to the constructor or the types of the arguments?
The arguments to the constructor. So the E would stand for, when we build a tree, the E would stand for the actual argument here. But, well, here you could say in a sense, you can see this also as a type case with definition, with the automatic definition of these elements, of these constructor elements. Yes?
Is there a way to specify a type that you want not to be extensible? Or a way to indicate that a match should fail at compile time if it is an exhaustive?
Yes, you write a sealed abstract class tree. That means all the cases have to be given in the same compilation unit. Yeah. Okay. Oh, very lively discussion. Let's see whether I get to the end of this talk in time. Okay, let's go to the second unification. The second unification is that we say functions are objects. So in Scala is a functional language, not in the sense that we don't have immutable data, that we don't have mutable data. We do have variables that we can change. We do have fields and all this. But it's a functional language in the sense that functions are very important. They are first-class citizens. In particular, every function is a value. And the second addition is we have the usual syntactic conveniences of functional languages that we say we give you anonymous functions, sometimes closures. We can have curried functions, and we can have nested functions. We can nest functions inside other functions, just like we can declare values of other types inside functions. And familiar higher-order functions are implemented as methods of standard Scala classes. For instance, here's the array class, which is actually a Java array class, but we do some magic to enrich it with more things. So our array class also has functions exists and for all, which are just the exists and for all predicates. So these can be used in things like this to find out whether a given matrix has a row consisting only of 0 elements. So let's dissect this statement here. It says matrix.exists. So call the exists method of matrix, see whether something exists in matrix, and then you pass in an anonymous function which says, is there a row such that for all elements of the row, the element is equal to 0? So what you have here is an anonymous function or closure. That's the parameter of the closure. Scala has fairly aggressive type inference so that you don't need to give a parameter type of this closure. And here you say row.forAll 0 equals. That means all elements in the row are equal to 0. So that's a partially applied function. So that's just the equals method applied to a number 0. Even primitive operations like equals are methods in Scala and not implemented as such. In fact, a Scala program would be implemented almost the same way as a Java program, and it would have about the same efficiency. But for the high level, for the type system and compiler, equals is seen as a method. So this is the application of the 0 method of the equals method to 0 with a missing parameter. So it means it's a function which takes an x and returns 0 equals x, right? To dissect that. So all this dissection, one gets used to it very quickly. And I think the bottom line is it lets you write very, very concise code. Yes?
It's nice if you wanted a column that was all zeros.
Sorry?
If you wanted a column that was all zeros.
I think you're right, but it would be quite possible to have a transpose method on the matrix. So we would say matrix.transpose.exists. And you could even arrange things that the transpose is done lazily, that you won't do all the transpose at once and then do it. OK? So now, if functions are values, and we've seen Scala as an object-oriented, pure object-oriented languages, so all values are objects, then it must follow that functions themselves are objects. And in fact, they are. The function type s arrow t, functions from s to t, is just shorthand for a standard Scala class, which is called Scala function 1 with parameters s and t. And here's the definition of that class. It's abstract class. Function 1 of 2 type parameters, s and t. And all this class has is an apply method. And the apply takes an x of type s and returns an element of type t. And of course, at this level, there's no implementation of the apply method because we're talking about the type of all functions. So you might...
Declaration-based variants?
Right. So these things are so-called declaration-based variants. That's a way to express that functions are covariant in their result type and contravariant in their argument type. If you don't know what this is, don't worry. It's not essential for the rest of the talk. It's just a standard convention that people want to have for functions. OK, so the bottom line is functions are interpreted as objects with apply methods. And here's a standard implementation. So that would be the successor function that takes an x of, let's say, type int and returns an x plus 1. So that would be expanded to new function 1 of domain int, range int, def apply x int equals x plus 1. So that's what the compiler essentially does with this. So that's what you get. And that's what currently you'd have to write in Java if you wanted to have something which is equivalent to functions. So you can write these things in Java, but it's more cumbersome. OK, so you might say, OK, good. So all this is one, yes?
So if a function is an object, what is a method of an object?
Good question. So that means you would have an infinite cycle, right? Methods are objects, and then they have an apply method. So methods are, in fact, not objects. Methods are primitive, but there is an automatic conversion that whenever you want to use a method name as a value, it gets converted to a function. But a method is just the same as a Java method. Only whenever you want to treat it independently, not just apply to the arguments, the Scala compiler will make it into a function object.
And so if I have an object, not just a class X, but an object foo, then foo.doit, is that essentially a closure with a pointer to its object foo? I see.
Completely right. Yeah. OK, so good. You might say, well, that's maybe a consequence of this design that if Scala is both functional and object-oriented. Is there any use of that? Why should I care about that? Well, one nice consequence of it, since the function arrow is a class, it can be subclassed. So it means that now function can actually be a root of a complete class hierarchy of specializations. And one of the specializations would be, for instance, the array class, the standard Java array class, which we treat, well, in Java, it's actually not a class. We make it into a class by reinterpreting some things. So an array would just be a particular function. Arrays are functions from integer ranges to whatever the element type of the array is. And they do have an apply method. So we can, that's just array subscripting. But they also have a method to return the length of the array. They have a method to change an element in the array, an update method. They have a method to give you back an iterator that iterates over all elements of the array. And they would also have things like exists and for all that we have seen in the matrix example. So exists would take a predicate, P. That's a function from the element type A to Boolean. And it will just tell you whether there is an element in the array for which this predicate is true. So one more bit of syntactic sugar that we do is that you can write things like that. A of I equals A of I times 2. And that really means A.update of A.apply of I times 2. Because the convention is whenever you have an object A and you use it as a function, you apply it to an argument, then the compiler will insert an apply method in here. It will do that anywhere in expression position. If you have the same thing at the left-hand side of an assignment, like this A of I, the compiler will insert an update for you. So that's some bit of syntactic wizardry that lets you write the almost usual array syntax, only with parents instead of brackets, and still reduce it to method calls. One thing that you gain with that is that you can do exactly the same things for your own sort of collections. You can do this with hash tables. You can do this with whatever. You can use just this syntax for selection and this syntax for update, which is quite nice. So we completely abstract from the concrete primitive type. Yes? The syntactic sugar, to extend the syntactic sugar, that depends in what ways, right? Not completely general. So we don't have a language which says, well, you can do whatever. But there are a lot of hooks in there, like, for instance, this hook here, like I said, it works for class array, but also for other things you might want to do, for other collections or other types that support similar interfaces. OK, another useful abstraction are, and less well known, are partial functions. So a partial function is a function that's defined only in some part of its domain. And what's more, we can inquire whether this function is defined for a given value or not. So the definition of partial function would be something that extends the function type, a to b, and it would inherit the apply method from this function type, but it would also add a method called isDefinedAt, which says it takes an element of type a and gives you back a Boolean, which tells you whether the function is defined at this thing or not. And one thing which is interesting is that Scala treats blocks of pattern matching cases, like this one. And if you want to see, well, what actually does this expand to, the answer is it expands to a partial function. So the compiler will take this pattern matching thing and will say, well, if I do not look at the T match, just this thing inside the curlies. What is this? Well, you might say it's a function. You give it an argument. If the argument is empty, it returns that. If the argument is a binary, it returns that. You can treat it as a function. And what's more, you can also find out whether it's defined or not. You just run the pattern matches without computing anything. You say, well, if it's that pattern or that pattern, you get back a true. Otherwise, you get back a false. So the compiler will actually translate this into one of these partial function thingies. And that opens up a whole new world of very interesting control structures that you can define, which are really not easily expressible otherwise. So here's one, which is something we have been playing with quite a lot recently, that involves concurrency, where one of the particularly nice abstractions in concurrency, I believe, are actors in the style of Erlang. Not sure whether people here know Erlang. It's been used for some pretty big telecommunication switches. It's one of the very, very few success stories where really concurrent programming has made it into big applications and seems to work reliably and seems to be usable by ordinary people. So what does Erlang have? Well, essentially, it has these actors, which are processes, and you have a message passing system. You send messages directly to a process, and that's done with syntax like this. Actor, bang, message, sends message to actor. And then you have a selective read, which is called receive, which is just a bunch of patterns. You say receive. So when a message gets sent, it's an asynchronous send, so it just gets queued in a mailbox of the actor. And the actors can then do a receive, which say, well, if I have in my mailbox a message which matches one of these patterns, then execute the corresponding action. And that's sort of all to get started with. So on the other hand, if no pattern matches, then the receive will just block until there are further messages that it can inspect. So here's an example of an actor written in that style. So it's an order manager, and you say that's an actor which loops and repeatedly does a receive. And if it receives an order, then the order would have a sender and an item, and you would handle it, and you would send an acknowledge back to the sender. And there would be similar things for the cancel thing. And finally, we would say, well, we actually want to treat all messages. We don't want to leave them in the message, in the mailbox forever. So there's a third catch-all case X, where X is just a variable name. So that matches any pattern where you just say, well, in any other case, I append the message to my junk file. And here would be a customer that interacts with this order manager by sending it an order message and then receiving back from the order message. If there's an acknowledgement, then things would be OK. Otherwise, in this case, the actor wouldn't expect anything else, and he would get a match error. That's just an example of what a typical programming style to do with this.
Mark,
Yes?
Does the case X thing actually declare that X variable?
Yes. It declares that variable. So to disambiguate constants from variables, there's the convention that variables start with lowercase names and constants should start with uppercase names. And the compiler goes to some lengths to actually give you nice error messages when it suspects that you have done things wrong and you want to use a constant, but you use the lowercase names. Okay, so they, of course, send. It's fairly easy how to do that. Well, you would just send it to an actor. An actor would have a mailbox implemented as a queue or something. You would just enqueue the message. In a shared memory system, that's how you would do the send. How would you do the receive? Well, we've seen now that the receive, it takes one of these case things. And these case things, they are partial functions. We've seen that. So what the receive actually would take here would take a partial function from some type of messages. Actually, message can be the same thing as object, can be anything. And A is just a polymorphic result type of the receive. So it's a partial function of message to an arbitrary result type A. And what do we need to do? Well, we need to look at our own mailbox. Self is a global variable that gives us the currently running actor. So we do self.mailbox. Extract first, that's a standard method in queues in the Scala collection libraries. And extract first extracts the first method that matches a given predicate. What predicate do we have to pass? Well, we have to pass a predicate that our partial function is actually defined for that message, which is just f dot is defined at. F is defined at means for arbitrary x, return f is defined at x. So that's exactly what we need. So what this thing would do is it would extract the first thing that matches, that for which the function is defined. And then the extract first is actually constructed. It gives you back another thing on which you pattern match, which is a so-called option type. So if it found something, it will give you back some of some message, and that's then the message you run the f of. If it hasn't found anything, it will give you back a none, which says undefined. And in that case, the receive would have to wait for another message to be sent. Yes?
What is the result of self.wait? Is it an A?
Right, so yeah, it would have to be an A. So there's something missing. You would have to then afterwards run the same receive. Very perceptive things. Yeah, so that's missing, indeed. Okay. So one possible objection to that is, well, you've sort of just duplicated what people did in Erlang. So why do that when actors are already in a purer, more optimized form in Erlang? And I think one good reason is that libraries are much easier to change than languages. So by being able to do these things in a library, it's much, much easier to experiment with things, to change things, to optimize things, to react to new developments. So one example for that is that both Erlang and the Scala library, the original Scala library, I should say, attached one thread to each actor. So every actor is a thread. And that can be a big problem for Java because threads are expensive. So it means you can't scale this over beyond a couple thousand actors, and some applications want more than that. Erlang is much, much better than handling many threads because it has a runtime system which is optimized for that. But even it can be overwhelmed by really huge numbers of actors. And what do you do if threads are too expensive? Well, you want to go event-based, right? So if threads are too expensive, you do event-based programming. And normally that means inversion of control, which means you have to completely rewrite your program, turn it inside out. That's not good. But if we actually implement actors the way we do in the library, it's quite easy to implement a variation of receive, which we call react, which liberates the running thread when it blocks for a message. The only restriction for the react is that when you liberate the running thread, then all that you will do when the message then finally comes has to be in this partial function. Afterwards, you can't really do anything useful because you have given away the thread. And we can express this in the type in Scala. So the nothing type means that you will actually not return from this function. Nothing is ever returned from the function. Another function that has type nothing would be a function that always throws an exception. So that also would have type nothing. Yes?
So presumably any enclosing try-finally blocks or synchronized blocks would somehow have to exit when this react happens.
Yeah. Indeed, that's done by actually raising an exception when this thing is. So there is an exception raised. So the client code is virtually unchanged between multi-threaded and event-based actors. And what you gain, you can see here, we did some performance tests. So it's a simple benchmark. You have a number of processes which you vary on this axis, and they just pass tokens around in a ring. And you measure the number of token passes per second in relation to the number of processes that you have. So Salsa is the current standard library for actors. It's somewhere down here. It's not very optimized, you can see. The original thread-based actors are here, so they're not very good. They go down. The native Java implementation is here, and the event-based actors are up here. So by going to this event thing, you can have virtually the same program, but get much better performance and much better scalability. So you see that this is virtually unchanged in number of processes, whereas even the native thread-based implementation goes down steeply after you push the processes beyond 2,000 or so over this on this machine. No, I can't explain it. I think on JVMs, there's a lot of things that we have really trouble to explain. Yeah. Okay, how much more time do I have? So 20 minutes. So I have to go a bit fast on that. So the third unification. Now, so far we have talked about programming mostly in the small. How can we play with functions, pattern matching, things like that. The last thing I want to talk about is programming in the large, where Scala actually has a quite clean and powerful type system, which gives you new ways to abstract and compose components. So what's a component? Well, this is just a program part that you want to combine with other parts in bigger applications or in bigger components. We want to see it. We don't want to tie it down further than this. And the requirement is that the components should be reusable. That means that you should be able to employ a component in a context different for the context in which for which it was designed. So to be reusable, a component needs interfaces. That's clear. And it needs interfaces to describe what it provides, but also to describe what it requires. Because if you don't do that, then all you have is an API, some big mass of software sitting at the bottom, and you can build on it, but you can't take something out of it and put it in a new context and tie it to new foundations. That's not possible. So true components need interfaces for provided as well as required services. And most current components actually are not very reusable. They're basically we just have APIs, not true components. And I think that has to do with the fact that most current languages are pretty good at specifying provided services, think Java interfaces, but they're not really good at specifying required services. In Java, how would you do that? Well, you just use it. Sorry? Yeah, but how do you say, well, I need that to run?
APIs.
Sorry?
An element of one interface, and you adapt it to some other interface. I mean, I understand that there's no native facility for doing it, and I acknowledge that it's great to have a language that provides this, and you'll tell us about it. Okay. But it's not impossible.
Okay, good. Well, I argue it's pretty hard. Looking at the experiences we had, let's go through the slides and then see what you have to say to it. Okay, so one other way to see this is that a component should refer to other components not by hard links, but only by the required interfaces. And if you push that to the extreme, then you would say you wouldn't have any statics whatsoever. No statics, because static data is a hard link. You refer to statics, you can't change it afterwards. Even static classes are troublesome because they are also hard links, global references to it. That principle is not new, but in fact, if you push it to the extreme, it's surprisingly difficult to achieve, in particular when you extend it to types and classes. So one language that has pushed it to the extreme is ML with the functor abstraction. And who is familiar with functors in ML? Who's comfortable with functors in ML? One. Okay, that's good. So functors are, well, I think to be fair, they are a bit clunky. They are really great, heavy-duty program abstractions, but you have to get your head wrapped around them. So what's the functor idea? the functor idea is a component is a structure, which is just ML's way of saying a module. And, but if it depends on other components, then it would be a functor, which is essentially a function from modules to modules. An interface of a component, the ML people have also, they just call it a signature. A required component then is a parameter to that functor. And composition is application of the functor to some arguments. So that's what they do. And then you need a problem with this, with the usual diamond problems that you have a functor here, it takes two things and they take another thing and you want to make sure that the other thing is the same. And that's done by fairly esoteric things called sharing constraints. So there's some shortcomings with this story that one thing you can't do is have recursive references between components because a functor can, of course, inspect its parameters, but the parameter cannot access the functor. And the problem is all big systems I know of want to have some recursive reference in there. So not having them is a severe limitation. There's no inheritance with overriding, so none of the object-oriented stuff. And structures are not first class, so you can't rewire them at runtime based on things that you know only at runtime. It's completely static, the layout of a module system. In Scala, it's different. So in Scala, we say a component is a class. An interface is an abstract class or a trait. A required component would be an abstract type member, or we can also do it with explicit self-types. We're going to see how that goes. And composition is mixin composition. So we have a generalization of the single inheritance plus interfaces in Java, where we say instead of interfaces, we can have so-called traits that can also have method implementations that can even have state, and we have mixin compositions to do that. So the advantages of the model is that now components instantiate to objects, and these are first-class values. We can support recursive references. We have inheritance, and we have very, very concise wiring because subcomponents are identified by name. We'll see an example in a couple of slides. OK, so if we look at how to express components or how to abstract over components, then I think in any programming languages, I think there are two fundamental ways to abstract over things. One is functional, the other is object-oriented. So the functional way to do it would be use a parameter. You don't know what it depends on, use a parameterize it. The object-oriented way would be to say use an abstract member, just postulate it as a member in the class. If you look at Java, then it's actually quite interesting. It supports both, but for different things. So why does it use parameters? Well, it uses it for non-functional values. So for plain values, you use parameters. You can't abstract over a value. You can't have an abstract value in a class. You can only have an abstract method in a class. So in our terminology, if you go to functional values, then you can't use parameterization anymore because values are not objects, but you need to use an abstract method. If you look at types, then for types with the generics, well, it's parameterization again, no abstract members. So in Scala, we try to be complete in that sense that we give you everything for all sorts of values. So for values, functions, and types, you have parameterization, and you have abstract members. You can choose anything you want. You might say, well, doesn't that make for a very complex language? Well, in a sense, yes, we try to be. On the other hand, we try to be very orthogonal. And conceptually, rather no, because we really play with this functional object-oriented duality that we can say we can express all sorts of parameterization as abstract members. So to be able, let's say, to derive a typing rules for parameters, we can actually say, well, what's the corresponding object-oriented abstraction rule, and then go back. OK. So here's a very simple program that uses that. It's the program, the class gives you a class of cells which have just a single value of type T and a getter and a setter. And usually you would say, well, we write this as a parameterized class. You can do that, of course, but let's use object-oriented abstraction because that's less familiar here. So what we do in object-oriented abstraction, we would say, well, this class actually has a type member T. So T is a member of this class. And it has an initial value also of this type T. So these two guys, they are abstract. We don't have an abstract keyword in Scala. You know that they're abstract just because there's an implementation that's missing for these things. And the other three guys are concrete. So the getter, setter, and the variable. So now let's do something with it. So when we can create a new abstract cell, then we have to just fill in the abstract things, as usual, with an anonymous class. And because type is abstract, we also have to fill it in. So we say type t equals int for this thing, and the initial value is 1. And that works because the types are compatible. And then you can write cell.set, cell.get times 2, and the compiler will figure out that this is all correct because it knows that cell has the type app cell where type t equals int. This is essentially a notion of a type refinement where you can say a type can be a class name, and you can have further identities of types or signatures for members in these things. Okay, let's do something more interesting. So far, we have only duplicated the parameterization thing. What we actually can do, we can also access app cell without knowing the type of its element. So here's one example that uses that, a reset method. So it would take an app cell and would set C to its initial value. And no, we don't even refer to the element type of this abstract cell. So why does this work? Well, if you look at the type of c.init, and that type is actually, what should it be? Here we say init is of type t. But of course, t makes no sense because t is local to this class here. So it's not even visible globally as a type. Every cell might have a different type t. So what we have to do is we have to use members. So the type of t is, the type of c.init would be c.t. So you can have types that have a prefix, which is a reference to an object. And the method c.set then analogously has type c.t to unit. Unit is our notion of void.
C.t can't change, I presume.
Right. We'll get there. Yeah. Thank you. So the formal parameter type and the argument type coincide, and everything is type correct. So generally, there can actually be more than one level of selection in here, but the type, the prefix here must be an immutable value followed by possibly some immutable field references. And at the end, you have a type T. So these things we call path-dependent types. So they're essentially the central innovation in the type system of Scala. That's essentially what the whole thing rests on. Okay, so why can we not allow these things to change? I probably don't have time to go into it, so ask me after the talk if you doubt it, if you think why can't we have types that change. So there's a slide which tells you why this would lead to type unsoundness. So, but let's look at an example where we use these things. And the example is a very real one because when I wrote the javac compiler originally, it wasn't very componentized. It was essentially had a lot of hard links in there. And when I wrote the Scala compiler, I used the same ideas. So it was essentially the same layout. So in a compiler in particular, you need to model symbols and types. And each aspect depends on the other. A symbol has a type. A type might be a class which contains symbols. So there's a recursive cycle. And both aspects require substantial pieces of code. So the first attempt of writing a Scala compiler in Scala defined two global objects, one for each aspect. So there would be an object symbols and an object types. And that defines a class symbol, and that defines a class type. And they refer to each other here. And they might also even have static data. OK, so that was the initial design. And it had several problems and shortcomings. The first one is they contain hard references to each other, symbols and types. So it's impossible to adapt one while keeping the other. Well, actually, I idealized a bit. The original version of the Scala compiler was written in Java. And these things would have been static data in the class symbol. But to translate into a Scala context, we did it that way. The second problem is symbols and types contain static data, and some of this data was even mutable. So the compiler is not re-entrant. Multiple copies of it cannot run in the same OS context, in the same OS process. And I think for the Java compiler, it was the same thing when I dropped it into Neil's lab. It was still had the same flawed design, and Neil had to do something about it to make it re-entrant. Because why does a compiler need to be re-entrant? Well, if you want to run it, say, as a plugin for Eclipse or another IDE, NetBeans or things like that, then it wants to run multiple instances of your compiler, one for a syntax check, one for a background build, say. So what do you do to make it reentrant? Well, the usual approach would be to say, let's, well, I think that the thing that happened in the javac compiler is that you say, well, let's just collect all this data, the static data, and put it into a so-called context object. And let's parameterize everyone with this context object. And then we're done. The one big problem with all this is that it totally breaks object-oriented encapsulation, because in this context object, actually, everything is accessible to everyone. So functional programmers would rejoice because they would say, well, I knew it, object-oriented encapsulation is a fluke from the beginning. It's not real, right? You can't really do real reentrant systems that way. But I don't think that's the end of the story. I think one can do better than that. So how can one do better than that? Well, the second attempt would be, let's just look at the reentrancy problem first. And of course, if we have nesting, arbitrary nesting of things, which we have in Scala, then we can put these symbols, objects, and types with the nested symbol class and types inside an enclosing class symbol table. And symbols, so because this thing is a class, it can be instantiated multiple times. Every compiler would have their symbol table with separate static data. So it would solve the reentrancy problem. But it actually worsens the component reuse problems because first, symbols and types still have hard references to each other. And second, they can't even be compiled separately anymore. They're in one big, huge file. So that's not really what you want. So the question is, how can you get more or less that, but still maintain separate compilation and different source files? So the third attempt is a component-based solution, where the problem is, well, how can you express the required services of a component? In that case, we'd have two, symbols and types, and symbols requires a type abstraction, and types requires a symbol abstraction. And the simple answer is, well, abstract over them. And what do you have for abstraction? You have parameterization and abstract members. But because these things are recursive, there's only abstract members that remain, because for parameters, we know no recursive references. So let's try abstract members. Let's put an abstract type in symbols and an abstract type symbols in types. So now they're classes, and each abstracts over the identity of the other type. So how do you combine them? Well, here's how. You write a symbol table and say, extend symbols with types. So that's the mixin composition we have in Scala. You can just take arbitrary classes that you define as traits, and you mix them in together. And what happens when you mix them in is that anything which is concrete will replace anything that's abstract in all the other participants. So if you go back, because there's an abstract member of type, but there's a concrete one here, the mixing composition will have this member. So there will be a relinking. So this reference will now go directly to this type. And for symbols, it will go the other way, because there's an abstract member of symbol here that will plug into the concrete member type here. So because we have this name-based identification scheme, it's very, very concise. We don't need an explicit wiring to say this wire goes here and that wire goes here. So it's all done by name. OK. So that's nice, and that would work. But actually, I lied a little bit, because in fact, what really happens here, you don't just want to postulate an abstract class type. In the class symbols, there would be a lot of operations on types. So you would say this type has to be implemented, at least a bunch of interfaces that you specified for types. And symbols is the same. So once you're done with specifying all these interfaces, then actually that's quite a big specification too. That's cumbersome to write all that down. So the question is there a more concise way to do it? And the answer is yes, there is. So what we do is we have something called required interfaces or self-types. What we actually write in the Scala compiler, we say class symbols requires, well, actually you can leave that out. You can write requires symbols with types, or you just write requires types. And class types requires symbols. And then symbol table extends symbols with types. So the question is, you sort of know what it means. This sort of means, well, I need the class types or a subclass thereof to be mixed in with me when I'm instantiated. And for types, it means the same thing. But the question is, well, can we give a more precise definition of what it means? And the answer, quite surprising, is yes, we can. When you write a class C requires T, then we call T a self-type. And the only thing that really means is that the type of this inside class C is now T. So you might say, well, isn't the class type of this the class itself? That's what it's usual. But if you think about it, there's no reason why this needs to be so. The type of this can be whatever you want it to be. It does not have, there's not a single good reason why it has to be the type of the enclosing class. Yes?
How do you avoid the dependency on the definition of T?
Well, there is a dependency on the definition of T, but you can change T later on.
Separately and
Yeah.
get checking anyway.
Right. No, you can. Well, okay. So the initial version has to be compiled together, but then they can evolve independently. Yeah. Right. Good question. Thanks. Okay. So without an explicit requires annotation, the type of this in Scala is just the type of the enclosing class, as usual. But you can say requires T, and then in that case, the type of this would just be T. So let's see why this works. Now in this thing now, the type of this here would be symbols with types, and here the type of this would be types with symbols. Actually, it doesn't matter. You can write symbols with types, types with symbols. In this context, it's the same thing. So then when you write here type, where does it resolve the identifier type? Well, as usual, when you have a member access, it's resolved to this dot member. So in the identity of the current object, the current object is a symbols with types, so it's a mixing composition of the two. So you say, in this mixing composition, I have an implementation of type here. So the type will resolve to this, and the symbol in the same way. So that's why it works. Okay. So, and actually, you can push this thing to UML kind thingies and have a required thing, but probably I skipped that because time is running out. So the benefits of this scheme is, it's very, very general. So you can take any combination of static modules and lift it to an assembly of components. You get documented interfaces for required as well as provided services. In this requires clause, you list exactly what you require. You can you get for free multiple instantiation of components, so you don't have a problem with reentrancies. And you can be very flexible in extending and adapting components. So there are a couple of slides that I skipped that show you how you could do that by adding a logging service to a compiler. And essentially, it all comes down just to, in the end, mixing composition. And that's all you need to do. So the bottom line is that a lot of the things that people think they need AOP for aspect-oriented programming now actually can be done much, much simpler using just mixing composition if you take it seriously that you say no static data and everything is an object. Yes?
So please comment on how true or maybe dumb this statement is. Is it true that mixing composition is essentially like using interfaces to express dependencies plus the ability to call the constructors of objects of these interfaces?
No, there's more because you compose classes that actually have concrete method implementations and might even have fields and variables. So it's more, there's a subtle difference between it and multiple inheritance. So it's closer to multiple inheritance, really. The difference is that supercalls work correctly for mixing composition. That means for mixing composition, a supercall chain would just thread through, whereas for multiple inheritance, it would not do the right thing. Yes?
Conclusion at the bottom of your slide is question. The point is, you have written more compilers, and as you rewrite similar code, you tend to write in type.
Right. So let me quickly say it. Okay, good point noted. So here's some summing up. Here some counts of compilers I've been involved with. So that's the original. That's the Java C pre-wildcards 1.5 Java C, a version which was sort of the thing when I gave it to Sun and didn't work on it anymore. So that's what was like the last count of lines of code. So I guess it probably is slightly bigger now. I don't know how much bigger. Then we rewrote the thing mostly in Java, actually using some pattern matching with it that already shrunk it a bit. And that was the first Scala C compiler. And then we rewrote the thing in Scala, and we got that. overall, it's true. It was the second version of the compiler. But overall, in the compiler history, that was like the 5th compiler I've written, and that was like the 4th. So I didn't get much better between the 4th and the 5th. I don't think so. So I don't think I learned a lot how to do it better. I think a lot of it was really that Scala really gives you ways to express yourself extremely concisely. And sure, I mean, you have to learn it, and there is a learning curve to it. But my claim is, and I have nothing to prove this claim, but my claim is that experienced programmers can become about twice as productive, use half as many lines, and be twice as productive as with Java today. That's just a claim that we can debate endlessly, no doubt.
Do you have numbers that aren't compilers? Very similar functional programming languages and compilers that are sort of made for each other.
That's true. That's absolutely correct. No, I don't. Unfortunately, I don't have really numbers of big other projects because we are in the compiler thing, and there are some companies using it for big projects, but they don't give us their source code, so we don't really know. So, okay. In the experience, I think the combination of FP and OOP has worked exceptionally well, better than we first suspected that it would work. Scala really lets you write quite pleasingly concise and expressive code. It's one thing which we didn't do. It's really great to do as hosted domain-specific languages. So for instance, I have an implementation of Prolog in Scala which looks to you on 95% Prolog. So it just looks like Prolog, but it's nothing but a bunch of library calls for a Java library, for a Scala library, which is itself just 100 lines or something like that. So it's very, very malleable syntactically, and it has a very, very strong abstractions underneath. So that's why it really works very well for domain-specific languages. And we made some discoveries, mostly on the object-oriented side, not on the functional side. So we've seen some of them, in particular the mixin composition, self-types, and the type abstraction. That was new. Yes?
There's another talk scheduled in this room at 2 o'clock.
I come to the conclusion now. Yeah, thanks. So to conclude, I've shown you a blend of functional and object-oriented programming. Overall, I think programming in Scala, for me at least, it has a similar feel than programming in a modern scripting language, but without giving up the static typing. And you can try it out on this URL. It's very user-friendly. So there's lots of documentation, very quick installs, and all that. And I'd also like to thank the members of the team who worked pretty hard on this. Thank you.